So welcome to the probably the 20th or 21st lecture on random processes. We have been discussing two important processes, the Poisson and the Gaussian. Yeah. So we have done some details about the two processes, and today we will continue with the Gaussian process. Yeah. So last time we defined the Gaussian process as what? Process where every linear combination of its variables and a variable inside it is also Gaussian process, or if it's a number, it's Gaussian distributed. Yeah, if it's a single variable. So we saw that last time, and I said there is an alternate definition for Gaussian process. So today we will do that, and then we will see once again the Wiener process, which we had seen as a limiting case of the random walk. Yes, which was a Markov chain. Yeah. So we had seen it as a limiting case of the random walk. Today we will see it as a special case of the Gaussian process. Okay. So as we said, Gaussian process is a stochastic process. Let's say a stochastic process or random process xt t in real number set t is a Gaussian process if every linear combination formed from these is
Gaussian
distributed Gaussian, right? So that was settled, and now we want to see what is it that happens. If we want to rewrite it, so this essentially also meant that every member here is also Gaussian distributed. Yeah. Okay. A second definition is that a stochastic process, let's say like this, T, is Gaussian if for every n and all selections of T1, T2 and Tn. So you can choose any subset of this random process, any set of random variables in there. They have to be, of course, in T, because that was the original limitation here. If for every n and all selections here, this vector, this is a vector of random variables, right? N random variables, right? So if this vector has, remember, a single random variable has what? PDF. If it's continuous probability density function. What about two or more random variables? They have joint distribution, right? So these are n random variables from this process. So they will have some joint PDF, right? That joint PDF, if that joint PDF is an n-dimensional Gaussian distribution. Okay, so I will explain it now. So far we have seen one-dimensional Gaussian distribution, right? So for a single random variable, let's say there is a random variable x, which if we say is Gaussian distributed with mean mu and variance sigma square. What is its distribution? The Gaussian one is 1 over square root 2 pi sigma square e minus x minus mu over sigma, and this whole thing is squared there's a half here also, yeah, e minus half, yeah. Okay, so this was the density function of a single random variable. If a single random variable has a density function that is that looks like this, or is this one, then we say that single random variable is Gaussian distributed. Fine. Now we are saying, let's say you take a set of random variables from a process, yeah, and that set has a joint PDF which is n-dimensional Gaussian distribution, and for the process to be Gaussian, for every selection of this you should get an n-dimensional Gaussian distribution. Okay, so what does that look like? What is the n-dimensional Gaussian distribution? So this has to have, we normally write it like this. I will need space, so I'll take this away. If we want to say that this vector has a joint PDF which is Gaussian, then basically we replace the mean with a vector mean. Okay, we could also replace this with a vector. Let's call that x, this thing, yeah, this underscore is the vector notation. In this case you could make boldface if you're typing, yeah.
It representing the mean of all the random variables.
Yeah, we will write it, yeah. So it's the mean, it's an n-dimensional vector, and it's the first value is the mean of the second, and then there is, instead of, in place of the single variance, now you have a matrix. Okay, and this is called now the covariance matrix. Okay, so when we say that a vector has a joint PDF which is Gaussian, this is what the Gaussian distribution, joint or n-dimensional Gaussian distribution looks like. This is saying, this was also small f, because capital is the cumulative, yeah. This is saying, remember joint में क्या होता था? Density, likelihood of first vector, first value xt1 taking some value from xt1, small xt1, and so on, yeah. So this, what does it look like? It is basically 2 pi n by 2 sigma, this is your covariance matrix, okay, square root of that, times e raised to e minus half x minus mu transpose sigma inverse x minus mu. Remember I said last time, when we go into joint PDF or n-dimensional PDFs, especially the Gaussian one here, we will go from scalars to matrices, yeah, vectors and matrices. So then you relate what happened. The single variable is replaced by a collection of variables, which is our vector, whose joint PDF we want to find, yes. And the joint PDF, if it is Gaussian, and dimension Gaussian, will look like this. So back to the definition of the Gaussian process. The Gaussian process is a process that if you take any set, okay, it can be 3 of those values, 10 of these values, any set or a vector of random variables from that process, and you see, okay, what is the joint PDF of these, and that joint PDF comes out to be the n-dimensional Gaussian, this shape, yeah, then you can claim that the whole process is Gaussian. Okay, it may happen that the, the set may not have a joint PDF that follows this formula. If it doesn't, then it is not Gaussian. Okay. So if you are able to write the joint PDF of any subset of the random process like this, in this form, like here, for Gaussian single random variable, if you were able to write the PDF of that random variable in this form, you said it is Gaussian, right? That is the definition of the Gaussian PDF. If it's a collection, if it's a random process, you have to prove that if I pick any one of them, I could pick 10 of them, I could pick 15 of them, I could pick 15 from here, 15 from there, or any other random order, any set that I pick from that process, and I look at its joint PDF. If I find that that joint PDF actually follows this formula, right, then I can claim that the process is Gaussian. Okay. So this is an alternative. What was the definition we saw last time? That was a random process whose every linear combination turns out to be a Gaussian variable or process. Yes. So it was like that, and here we are now defining it in terms of an n-dimensional Gaussian distribution. Okay. So it's not too. It's actually very analogous to the single random variable, except that now, firstly, we talk about the joint PDF that should have a shape, which is this guy. That's one. Secondly, just in case of single variable, there is only one thing. Yeah. In case of process, the JPDFs can be calculated for different subsets. All of those should follow the Gaussian. So if you take 3 of them, then it should follow a 3-dimensional Gaussian PDF. If you take 4 of them, it should follow a 4-dimensional. Of course, which ones you take, according to them, this mu and sigma may change. That's fine. We're not saying. Of course, if one of you picks, let's say, this is a random process, yeah? If we want to show it's Gaussian, if one of you picks 3 values here, 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 yeah? This is xt1 now for you, xt2, xt3, and their joint distribution fits in here. It will have its own, they will have their own mean and covariance. That's fine. It's the shape that should. If I pick another 3, I pick this one, and this one, then there is no requirement that the first one and the second one should have exactly same values here. We're not saying that. We're saying this shape should be the same. Okay, it should be Gaussian. It should not turn out to be some uniform, some exponential or some other shape. It should be this shape or this model.
And so what it represents is the same, if they are in the same model, that the whole distribution of 2, 3 or 4 is also Gaussian. That represents this phenomena. मतलब ये फॉर्मूला में यही रिप्रेजेंट करता है कि हम 2 ले लें, 3 ले लें, 4 ले लें, तो हमारे पास सेम मॉडल कंस्ट्रक्ट हो रहा है.
Yeah. So
there is actually a mathematical way to define the third condition, that every linear combination. You can say that in that sense.
Yes. In this case, we are not combining them. We are still writing them as a vector, right? So there we were either summing them, integrating them, or averaging them, those things. Here we are talking about the joint
Distribution.
PDF, right? So it's a bit different from that. Yeah. Again, there is no requirement for, let's say you have a process and you find that 3 of these, you take, let's say, some 3 of them or 4 of them, and their distribution, their joint distribution turns out to be not fitting in this formula, then that process is not Gaussian. Okay, and of course you cannot pick a few values and show that, okay, now because there's infinite number of combinations. Yeah, so normally you have to show that theoretically. Yeah, so There are different ways of making those assumptions, but essentially this is what you will need to show. Okay, right. So another way of saying it is that a Gaussian process is a process in which any subset follows the joint Gaussian distribution. So, simpler हो गया अब, right? Any subset लें उसमें से और वो that should follow a joint Gaussian distribution. Yeah. If you take a single variable, then this will collapse to this thing. Yeah. So that is also fine. Okay. So I haven't written the, what haven't we written? X, small x, what would that be in here? Small x would be the values we want to study here. Small x t1 up to small x t n. Like here, you say what is the likelihood that x takes the value small x. Here we are saying what is the likelihood that the vector takes this vector value, meaning now you do element wise. Yeah, what's the likelihood that x t1, the first member, which is a random variable, takes this value, it can be 10, 9, whatever. Yeah, what is the likelihood that the second member, which is a random variable, takes the thing. So now it is element wise between vector. That's one thing. Second, instead, in place of now a single mu, which was the expected value of x, right? Now you want the expected value of the vector. So it will be expected value of xt1, expected value of xt2, and so on, which we represent by mu. So I'm just going to call it this thing, expected values of element wise there. Now sigma is the most interesting. What would sigma be? Any thoughts?
Summation of some.
So it's a covariance matrix. Remember, when we go from single PDF to joint PDFs, we start coming into covariances, right? So here sigma is represented or is representing basically, this is not the page we want. Yeah, okay. So let's make space for sigma. Maybe over here. So sigma is remember the vector I'm talking about is xt1, xt2 up to xtn. Yeah. So this is the covariance of xt1 with itself, xt1. Yeah. Then you do covariance of the first random variable in the vector with the second one. Yeah, and so on. So basically, if you remember now, we had this set. These were the random variables we picked from the process, right? What you're saying here is the covariance of, you start with one of them, you say the covariance of xt1 with xt1, which we have already expressed is the variance. Yeah. So you start here. Then you say the covariance of xt1 with its neighbor. That goes here. Then the covariance of xt1 with its second neighbor. That goes here. You go all the way to the last guy in the vector. Then you come back and do what?
The second.
Then you pivot on the second one, xt2. Yes. And you say okay, covariance of xt2 not with itself first, always with itself. So then their own covariance will be along the diagonal, right? Yeah. So it has a structure, and you can also see that it will be symmetric. Why is that? Because RT1 T2 should be RT2 T1. So covariance of XT2 with T1, which is RT2 T1, which should be RT1 T2. Here it's the covariance of now T2 with itself, which is its actually variance of the second variable, T2 with T2, and so on, T2 with Tn. So you can imagine what will happen here, Tn with what? T1, and so on until R Tn with itself. Yes? So the diagonal is the variances of each of them, whereas the off diagonal values are covariances. As you go along this, you are talking about covariance with the next neighbor, the further next, and so on. Yeah. This is the called the covariance matrix. So now you have gone from variance, and we did covariance for two random variables. Yeah, that was, we had done that like we did for x and let's say y. Remember, covariance define kiya tha na humne?
Yes.
We didn't need a matrix there because it was just one covariance. Now we are talking about any set. So we want to have something general. If you are talking about just two random variables, then this can come simpler. But now here it is a covariance matrix. Okay, and this word covariance matrix shows up a lot, and is one of the key things that people work with when they are applying random processes, random modeling to most of our modern problems in communication, speech processing, image processing. मैं आपको बहुत easily I can tell you that this is a topic, or the covariance matrix estimation, or using it in the estimation, is like the bulk of the work that we do. Okay, and again it relates to what I said very early on. When you're dealing with random processes, the ideal thing to deal with is their, or random variables also, is to deal with their PDF. Yes, PDFs can be hard to work with. We replace that with first and second order moments, which was mean and variance, or for multiple two variables it was covariance. But for more than two variables, meaning random processes, if even covariance isn't enough, you go to covariance matrix. But essentially you are still doing the same thing, that you are working with second order statistics, right? So that's why this word is important, covariance matrix. No matter if it is showing up in the Gaussian distribution or somewhere else, it's not restricted to Gaussian distribution. In the Gaussian distribution, it shows up in a very special way, here and here. But it can show up, or actually any process coming from any distribution will have a covariance matrix. Okay, so as long as it's a process, yeah, and there is no restriction on the shape of this process that is for Gaussian. It's this definition. That's it. It's for any process. You don't have to say that the process was Gaussian. Yeah, but if this covariance matrix fits in some formula here like this, then you're talking about the covariance matrix of a Gaussian process. Okay, so now there is one important assumption here for this whole thing to hold. Yeah, we're saying that the covariance matrix of, or the the distribution, the joint PDF of the vector should follow this formula. If it does for every vector, then you say the process is Gaussian process. Yeah, what is the assumption? Here there is an important assumption for this to work. there might be situations where you might not be able to test this thing. Okay, matrices में एक मसला आता है कई दफा, normal में भी आता है लेकिन matrix especially you see that.
Determinant zero.
Yes, exactly. You can see it in here also. You need it inverse here.
Yes, sir.
Yeah. If this covariance matrix happens to be non-invertible, yeah, then you will not be able to show that things fit in this formula because the sigma inverse won't exist. Okay, in that case we say that the process or the vector has a singular distribution and its PDF does not exist. Okay, so that's one special case, but usually it doesn't show up, so we will not worry too much about that, but it's good to know it.
ये जो हमारे पास तुमने x वेक्टर लिखा है जिनमें ये लिखा हुआ है xt1 xt2 xt we are saying that x small xt1 belongs to capital xt1. ये हम इस तरह कहना चाह रहे हैं स्मॉल xt1 जो हमारे पास है, हमारे पास जो रैंडम वेरिएबल्स है कैपिटल xt1 उनसे बिलोंग कर रहा है और ये उस कैपिटल xt1 का कोई भी हमारे पास हो सकता है मेंबर.
No, you have to go back to what we did very early on, which was saying let's go to rolling a die, right? So let's say this first variable xt1 is the first roll of the die. Yes, so when we talk about the PDF of this thing or mass function of this thing, what are we saying? That x, this guy can take how many values? x1, x2, x3, x4, x5 and x6. That is the small x. याद है वो universal set के अंदर वो the events that you have, those are the small x. The capital X is the variable that represents the random event. Yes, the values it can take from its universal set, yeah, those are called, we just label them small x. Why small x? Why not 1 2 3 4 5 6? Because we want to keep it general. I know for dice I can say I know this is 1 2 3 4, so we say what is the probability that x takes the value 6 for a dice. You can say that, yeah, but how do you make this general? You will say what's the probability that x takes the value small x, where small x is in the universal set. If it's not in the universal set, you already know this value will be 0, right? The probability will be 0. So likewise these small x's are not some sort of specific value. They're saying what is the probability that capital xt1, which is a random variable, takes this particular value, whatever you want to put here. Okay, so it's not subset or anything, it's just what outcome you want to see. So let's say I want to say that what's the probability or the PDF. If we're talking about the PDF of fxx, this thing, we're saying what's the relative likelihood that x takes the value small x. If we go to vector, we are saying what's the relative likelihood that each element in x takes the values in each. That's why it's a joint distribution. Why? Do you see the and in there? And where's the and? What's the likelihood that the first variable takes the first value and the second variable takes the second value, and because of those ands it's a joint distribution. पीछे वो आप दोबारा जाएं, आप connect करेंगे, yeah? थोड़ा सा I know it can be a bit tricky, but इसीलिए we spent a good deal of time on all of that developing. So once you start connecting, inshallah आपको you won't find it too hard. But answer हो गया, clear हो गया?
Yes, sir.
इसका वो मतलब है कि जी what is the outcome you want to see. Yeah. Now, because we are talking about definitions, we want to keep it general. You might say I want to have the first variable taking 0.5, second taking 0.9, third taking 1, so on. You could say that, fix the numbers. But we are talking about currently general definitions. So there we have to restrict ourselves to mathematical notation that allows any general values, right? So that's what we're talking about. Okay. So um, now some interesting properties of the Gaussian process. I'll just talk about one interesting property. I've already mentioned this briefly, but it's good to see it here. We had strict sense stationarity and weak stationarity, right? So for Gaussian processes, if you can show that the process is weakly stationary, it will also be strictly stationary. Okay, so if it is weakly stationary, it will also be strictly stationary. Why is that? I mentioned this before, that for a Gaussian process, we saw for the Gaussian, yeah, for the process, basically the moments of a Gaussian uh, single random variable, also higher moments can be written in terms of first and second. Yeah. So now let's see how that translates into a Gaussian process being stationary, strictly stationary if it is weakly stationary. So the statement is a weakly stationary or weak sense stationary Gaussian process is also strict sense stationary. Okay, this does not hold true in general. Okay, so but for a Gaussian process, if you can show that it is weakly stationary, it will be and that really helps us, because that means we only need to, for a Gaussian process, we actually only need to study up to second order statistics, because the rest is just following similar. So let's start. Let's say there is a process, let's say there is a Gaussian process, and we know that it is weakly stationary. Okay, then what do we know about xt? What conditions does it meet? Mean is constant. So if I want to say that this has a mean xt is actually, yeah, no need for a t, yeah, so that's what else, second condition, covariance. So let's say of any of these t, and a shifted version should be only dependent on, no need for t here either. Actual t doesn't show up in either of these. Yes, that is the requirement. This is, let's say there is a Gaussian process for which you know that it is wide sense stationary. That means you know these two hold. Now can you say is the process also strictly stationary? In general you can't. Let's see what will happen with Gaussian. Remember the distribution that I just wrote for the Gaussian joint. Now this process, since we have already said it is Gaussian, yeah, I'm not proving that it's Gaussian. We had already said it is Gaussian, and we said it's wide sense stationary. So since we know it is Gaussian, I can say for any vector in this, its distribution will be the n-dimensional Gaussian, which we have already written. I will just quickly rewrite here: sigma half e minus half x minus this mean x, which I had previously written as, I'll still write it as mu, you will see, and sigma inverse x minus mu. Yeah, you know in matrices this transpose thing is the equivalent of the square, right? पहले वो आता था ना यहाँ पे सिंगल में क्या था, e minus half x minus mu over sigma square. Matrices में you know, xt time, if there's a vector xtx, it's a column vector, this becomes the sum of the squares. Yeah. So anyway, right, this is what the distribution will be, right? No confusion on that, because I already said it's a Gaussian process. Now let's bring in this information, new information. The new information is that the Gaussian process is also, by sense, stationary. So we know, okay, how will the mean look in this formula? What did this represent? The mean of xt1, the first one in the vector, and this can be any vector you pick from here. Yeah, but you know now what will be the mean here for the first one. So let's say this is a vector uh, taken from here. Let's call this, just for convenience, xt1, xt2 up to xt, and let's say, yeah, okay, because it's Gaussian, yes, any vector taken from here will be following this form. Fine. What is in this form? The mu is, the mu vector is the vector of the means. Mean of this, mean of this, mean of this, and so on. Yeah. So what's the mean of the first one?
mu1, mu2, mu3, m1, m2, m3.
Mu1. Generally, yes, but now you have some extra information.
Constant is वो 0 होगा सर.
No, the mean is fixed.
Yes sir. Same होगा ना सर फिर तो.
Yes.
m1, m2, m3.
Yeah. M1, M2, M3 is very
मतलब m होगा ना.
हाँ, m कह दें, mx कह दें, t हटा दें बस उसमें से. Right? First one, number. Yeah.
Yeah. वो नहीं सर, मैं वो ना 0 इसलिए कहता हूँ, मैं उसको समझ रहा था, नॉर्मल वाला केस समझ रहा था.
हाँ, स्टैंडर्ड गॉसियन की बात. हाँ, उसमें 0 होता है, लेकिन स्टैंडर्ड तो ये है ना. राइट. ओके, व्हाट अबाउट सिग्मा? याद है सिग्मा की डेफिनेशन अभी लिखी थी हमने. इट्स द कोवेरियंसेस. यस. सो लेट्स ट्राई दैट. तो क्या बनेगा उसमें? आई जस्ट राइट द
कोवेरियंस हमारे पास. सेम कोवेरियंस हमारे पास 0 हो जाएंगे सर.
0 हो जाएंगे, r 0 हो जाएंगे.
R of t1 and t1 is going to be 0.
Now, because it is wide sense stationary, we have this information. So try now r t1 with t1. What is tau?
0.
0. So here you will put r 0. Before you couldn't put that, basically, yeah, because you were talking about general Gaussian process. Okay, what was here? R t1 with t2. T1 with T2 will be some gap between them. Yeah, we could call that, if it is, let's say, unit gap, or if you want to just denote it here, you can write it in terms of the difference between the times. Yeah, so on, and you could go up to, let's say, Rn minus 1, and basically here it will be R1, Rn minus 1, 2, and diagonals are all R zeros. Yeah, but the thing to note here is this: even if you don't want to write exactly like this, you could write it as the difference is, if you put these back in here, yeah, does time itself show up anywhere in the whole joint distribution? अब आपने, you put this m, the mu vector here, and this covariance matrix here, right? The time itself, t, does not show up, right? Only the lag will show, and here no time anyway. What just happened? The whole distribution you are showing doesn't change with time. है ही नहीं उसके अंदर वो t है ही नहीं है. तो you could have picked these from the start of the process or the end of the process or the middle of the process. As long as their internal lags are the same, their distribution, whole distribution is going to be same. And isn't that the definition of strict stationarity, that the full distribution should not depend on time? Its easier version was, okay, it's hard to talk about the full distribution. What did we go for? First and second moment, which was called weak stationarity. But for Gaussian, if you can show it's weakly stationary, you can also prove that it is fully stationary or strictly stationary, because weak stationarity will lead you to always lead you to a joint PDF, which itself has no dependence on time. Okay, so then basically this claim holds true.
मेरी diagonals वाले हमारे पास 0 हो जाएंगे R0
ये वाले करके देखेंगे कोवेरियंस
मीन सेम है ना सर हमारे पास
है,
मीन सेम है कांस्टेंट है हमारे पास ये वेरिएंस ऑफ t1 के इक्वल होंगे तो एक्सपेक्टेशन ऑफ t1 स्क्वायर माइनस एक्सपेक्टेशन ऑफ t होल स्क्वायर फॉर्मूला लगाएंगे तो 0 हो जाएगा m स्क्वायर माइनस m
वो अब मैंने सेंट्रल और नॉन सेंट्रल से मिक्स टाइप कर रहा हूँ. यहाँ पे नॉर्मली दे शुड बी लीडिंग टू देयर वेरिएंस. Okay, so what is the variance?
r of xt1 r of xt2
एक ही होगा ना.
वेरिएंस ऑफ x of t1 वेरिएंस ऑफ x t1 है सर हम निकालेंगे तो ये एक्सपेक्टेशन ऑफ x of t1
नहीं वो आप before you calculate anything else, you agree कि the diagonal will be the variance of the xt1 variance of xt2.
सर वो xt1 का हो या xt2 का हो मतलब हमारे पास मीन्स तो सबका सेम है ना
नहीं वो ठीक है, वेरिएंस आ रहा है डायगोनल्स में,
डायगोनल्स में सर वेरिएंस
वेरिएंस आ रहा है राइट. एंड यू वांट टू रियली कैलकुलेट कि किसी रैंडम वेरिएबल की वेरिएंस 0 हो जाएगी.
सर हमारा कोवेरिएंस ये डायगोनल्स वाली 0 हो जाएगी.
हाँ
r of 0 0 हो जाएगा.
वेरिएंस का फार्मूला लगा देना. ऐसे आप कह रहे हैं डायगोनल इज वेरिएंस ऑफ x1, दैट्स इट. क्या व्हाट्स द फार्मूला ऑफ वेरिएंस?
एक्सपेक्टेशन ऑफ x1 होल स्क्वायर minus expectation of
basically isn't it expectation of x minus mean of x
yes sir
whole square.
दूसरी टर्म में लिखा था मैंने सुना एक्सपेक्टेशन ऑफ x स्क्वायर वो डायरेक्ट फॉर्मूला होता है हमारे पास माइनस एक्सपेक्टेशन ऑफ x का होल स्क्वायर.
Yeah, so what does that come out to?
So expectation of x square is going to be m square minus m square n square 0.
So the central and non-central moment you have, basically it will be the variance here, right, which is r0. Let's test this here, covariance of x1 with x1. Yeah, so you have the formula for covariance we have, उसको apply करके देख लें. Most likely I think you might be mixing it with the non-central moments जिसमें वो mean you remove it. Yeah, so we can check later. Just try this. Okay, covariance of x1 with x1. Okay, the thing that you're saying the mean will be the same is, we're not talking about two here, is the same random variable, right? So covariance of x1 with x1. Yeah, so उसको आप चेक कर लें कि क्या बनता है उससे ना, फॉर्मूले से क्या आता है उसमें. Right, so then we move on to this thing that is the Wiener process, and कुछ याद है क्या था Wiener process? It was
Markov.
yeah. So how does that connect here? We'll just mention briefly how it is, or that it is a special case of Gaussian processes.
First of all, Markov process था सर, then Markov chain, फिर उसको Brownian motion, फिर Wiener process. Random walk था, random walk का फिर Brownian
Right.
motion to Wiener.
So our random walk basically started by saying that you have something that is right recursive definition. It's from its previous state. The new state is the previous state plus some change, right? And for the random walk, the change had a special form. We said, let's say the ith change was either delta or minus delta, right? With this was probability half, and this also probability, meaning they are both equally probable. That was one thing. Secondly, all the xi's were what? IID. They were independent and identically distributed. So this is the distribution. If the deltas don't depend on I, you are already saying they are identically distributed. They have uniform distribution, but it doesn't cover the part of being independent. Here it is now covered. It is IID and uniform with two possible values. Yeah. If you had this, we had said that okay, that becomes kind of a random walk. And then we saw that, or we discussed that the limiting case where if you we had this, yeah, the random walk thing, right? ऐसे था ना कुछ? Yes. And you were allowed some fixed h, and this was the delta plus delta or minus delta. Then we said as h goes to 0 and delta delta goes to 0 and n goes to infinity, you're allowing it to go on. Then Sn, the limiting case is a continuous process which we called Brownian motion or Wiener process. And what did it look like? Because you made this thing continuous, it looked like, right? जैसा हो गया ना? Yeah, so that was the Wiener process. Now here I just want to mention that it is in fact a Gaussian process, and it can be defined in another way also. You can reach, this was one way of reaching the Wiener process as a limiting case. Another way is very similar to the Poisson process, and that's the reason I wanted to show you here. That is, in Poisson process what we're doing, counting, yes, and the what was the requirement that the increments we saw, what did they have to follow? They were independent increments, right? Stationary and simple increasing. Yeah, so that covered everything. Simply increasing increments, yes, or simply increasing property the process had. Yeah. So we will redefine the Gaussian process in a similar way. The Wiener process. So a Gaussian process, let's say xt with t in 0 to infinity, is a Wiener process if it follows the following conditions. This one was also there in Poisson. I forgot it, that you have to start at 0, and that's so that you don't have a previous count. It starts at 0. Second, the increments are independent of each other. Okay, so independent increments. That means if you take any non-overlapping set xt2 minus xt1 and then xt3 minus xt2 or any other, the increment in this period, the increment in this interval, any set of intervals that are non-overlapping, the increments in those will be independent of each other. So we discussed this last time in detail about Poisson, so I'm going a bit faster. Basically, non-overlapping intervals have independent increments, right? That is the increment thing. Thirdly, this is interesting one here. The increment, any increment xt plus h minus xt, this increment has normal distribution. This is where now it starts referring. Yeah? So the increments have normal distribution. What is that normal distribution? Basically, we're saying that this increment, each increment is distributed normally with zero mean and a variance that is a function of the width of the interval. Okay, but the important part here is actually this one, that each increment has to be Gaussian or normal distributed. Okay, if a process satisfies these conditions, then we say it is a Wiener process. Okay, now notice that we didn't say that the Wiener process itself is Gaussian, right? So we just started here. We say, okay, there is a process that has x0 equals 0. It has independent increments, and each of its increments follows Gaussian distribution. Then what about the process itself? Can you show that it is Gaussian? Xt. What will be the distribution of xt? So let's say I haven't given you this thing. I just said a stochastic random process, yes, like this, that follows these conditions, is Wiener process. Okay. Now I want you to argue that any process that follows these three will essentially be Gaussian. No, this is definition for Wiener. So notice here I've only talked about the increment being Gaussian, right? So what is the distribution of xt? If you can show that the distribution of xt is Gaussian, then you have shown that, because xt is Wiener process, right? So then Wiener processes are Gaussian processes by necessity.
Select sum of the random variable, set of random variables, and prove that the sum is inside the set, then it will be a Gaussian process.
Yeah. Let's do it like this. Can I write this basically? Can I trick this to say that this itself is an increment? Can I say that? Is it? What is the size of the interval? See, every increment has to be Gaussian, right? And the mean will be 0 and the variance will be sigma square times the size of the duration. Can I write any xt like this or no? In this case, here x0 is 0. What is the width of the interval here? T. And this is an increment that happened from 0 to t. It has to be following this distribution 0 and sigma square t. Yes? By what? By necessity of these two. It should, yes? So, yes, xt is Gaussian. The process itself, not just the increments now, the process itself is Gaussian, because at any given point it can be seen as the total increment over 0 to that time. Yeah. So basically the Wiener process is a Gaussian process, okay, by virtue of this definition of the Wiener process, okay, right. Then we can try to find the, you already know the mean of the Wiener process. What is it? Of the Wiener process. So I will remove this now, and this is the distribution of the Wiener process. Yeah, mean is 0. Variance is increasing linearly with time. The sigma square will be some fixed value, but as time increases, the variance is going higher and higher. What about the covariance of a Wiener process? I just want to mention it because it will come out to be very similar to what you already saw. Remember, the covariance of a Poisson process was lambda square min st. इसका भी वही है, लेकिन now there is a different variable sigma square here. Okay. So what can you say about stationarity or non-stationarity of a Wiener process? Do you think it's stationary? है? Stationary? या नहीं है? No? कर रहा है? इधर variance भी depend कर रही है. But if you want to track the covariance, first mean you cannot say anything from here. क्योंकि वो है 0 तो क्या करें? है constant fix है 0. Variance is time dependent, so you already know, you don't need to check the second condition. But if you wanted to, you have the second condition. Does this depend only on the difference of s and t, just like Poisson process? No, it wants the actual values. Otherwise, सिर्फ s minus t में अगर आपको बता दूं तो min तो नहीं निकलेगा ना उससे minimum, right? So it is non-stationary process. Yeah. So some other important interesting things about the Wiener process. It is special case, limiting case of the random walk, which is a Markov chain. It is a special case of Gaussian process. It is everywhere non-differentiable. I'm not proving it here, but it has very special properties. Yeah. So at any given point, it cannot be different. It has its difference or its derivative does not exist. Okay, that's one thing. Third thing, it is always irregular no matter what the magnification. Okay, so if you want to zoom in, if you draw it on much finer scale, it will still look irregular. Okay, on all scales. Thirdly, it belongs to an intersection of 3 kinds of processes or 3 classes of processes. So Gaussian processes you have, okay, and then you have, let's say, self-similar processes, and you have Levy processes. Okay, where the 3 intersect, this one, this is the, or at least Wiener process falls in here. I don't recall, we could do some homework to see if there are other processes in this place. Yeah, but one of them at least is Wiener process. So Wiener process is Gaussian, it is self-similar, it is a Levy process. I will briefly mention, I just want to mention these titles and one definition of Levy. Self-similar process, kabhi suna? In stochastic variables or processes, a self-similar process is that if you zoom into the process, okay, no matter how much you zoom in, you take that zoomed in thing and you look at its PDF or statistics, that turns out to be the same as the statistics of the zoomed out one. Okay, let me चलिए लाइक वो फ्रैक्टल्स नहीं होते chaos में जितना अंदर जाते जाए यू फॉरगेट कि आप कितने अंदर हैं क्योंकि उस फिर वही चीज़ रिपीट होती है.
पैटर्न भी सर यूट्यूब पे इस तरह से कि देखे थे हमने कि उसको जितना अंदर जाते हैं उसी तरीके से रहते
वो फ्रैक्टल्स हैं ना chaos थ्योरी के हैं वो या कुछ कुछ वही है लेकिन दे आर नॉट टॉकिंग अबाउट द स्टैटिस्टिक्स दे आर टॉकिंग अबाउट द पैटर्न हियर वी आर टॉकिंग अबाउट द statistics. So I'll write very briefly. Let's say a very brief definition of a self-similar process. Let's say there is a stochastic process, 0 to infinity. Let's say there is some stochastic, no conditions put on it so far. Okay, we will call it self-similar if for all n, any n, and lambda greater than 0, we will use it, and some and t1 t any tn any set you want to pick from here, from inside this, just like the Gaussian process, you're picking some subset, right? The vector you get, the random vector, let's say lambda minus h x, is capital X, lambda t1 and lambda minus h x lambda tn has same distribution. Let's say you theoretically find the distribution of this thing has same distribution. I'll explain it in a bit. Let me write it then I'll explain. xt1 xtn. Okay, so this is the original. Yeah, let's say you pick t1 t2 tn and so on. Okay, this is a vector you get. Yeah, it has some distribution. Let's say that distribution is, I will call it, let's say fx x. Yeah, okay. Now if you can prove that if I scale, ये scaling होती है ना मैथमेटिक्स में होता है फंक्शन को, lambda is greater than 0, right? So I am scaling this thing, I am zooming in, yeah, or zooming out, depending on if it's fraction, it's bigger than 1 or smaller than 1, depend करता है ना, दोनों आप zoom in भी कहते हैं zoom out, but it cannot be negative in this case, okay? Then you're just going somewhere else. Yeah, otherwise if it is greater than 1, you are talking about what? You are zooming out. Yeah, so so on. So if the zoomed in or zoomed out version of this vector also has, let's say, its distribution for a given lambda, or for actually every lambda turns out to be, let's say it turns out to be gx x, and if the two are same, then we say that the process is self similar. Okay, so essentially if you had, let's say you had a process, yeah, and you picked value here, here, here and here, yeah, and now that was going to be these ones, let's say. And let's say you zoomed in, and instead of picking 4 values like this, you picked up 4 values, because you're zooming in, you're reducing the gap, so you picked out 4 values, like say here, here and here, you zoomed into the process. Yeah, and if the distributions you found was the same as the original, then we say that the process is self similar. Okay,
हमारे पास T1 T2 T3 T4 अगर हमने लिया है लेट्स सपोज, मतलब फिर उसको हमने जूम किया तो उतने ही डिस्टेंस से हमने वो पॉइंट्स लेने हैं उसके, मतलब इनका डिफरेंस उतने ही डिफरेंस है, तो वैसे तो कोई भी पॉइंट लेंगे तो डिफरेंट हमारे पास हो सकता है ना सर.
yes, yes. So if you look at this here, let's try this. So let's say this is 2, let's say, right? So originally you had taken xt1 xt2 xt3, now you are taking x twice t1, yes, if lambda is 2, and x twice T2 and x twice T3, right? So the difference, the gap can vary in this case. Yeah, essentially, whatever you had before, now you are picking values that are at twice of that. Okay, so if you had picked them at 1 second, 2 second, 3 second, let's say, now you are picking them at 2 second, 4 second and 6 second, right? So the gap has increased in this case. You could reduce the gap also, and we're not talking about just 2 or 1, 2, 3 or some value. We're saying for every lambda greater than 0, if you can prove that this vector has the same distribution as the original, then actually you've proven that is self similar. Okay, and what is h here? That is called the order of self similarity. So if you can find what order this for what there might be a process that satisfies this condition for one value of h but not for another value of h. Okay, so that is called the order. I don't want to focus too much on it. Wiener is a self similar process of order half or index half, but we don't need to go into that right now. Just think of it this way, like the fractals you see. Yeah, if you zoom into that process, you have a random process, you zoom in or you zoom out. In this case, what happened, by multiplying by 2 we zoomed out, right? We saw bigger gaps, but we still found the same distribution. Okay, and if you zoom in and you take those values there and you find the distribution is still the same as the zoomed out, that is called a self similar process. Okay, so interestingly, Wiener is a self similar process. Okay, I'm not proving it here. It has been proven that for a Wiener process you can show that for h half, h chosen half, this property holds. Okay. Thirdly, the very last thing here, the Levy process. It is also a Levy process. And what are Levy processes? We don't need to spend too much time on them because we have already covered the real thing, so it will be so fast to define the Levy process. First, let's define what is a Levy process. Okay, a Levy process definition is very similar to the second definition of Wiener and the Poisson. Yeah, any process, any stochastic process. Again, we start here, t0 to infinity, is a Levy process if it has it satisfies these conditions. Recognize this, it's in Poisson, it's in Wiener. Second, it has stationary increments. Okay. Third, its increments are independent. So any process that follows or satisfies these conditions is a Levy. That is the definition of Levy processes. What was the definition of Wiener different from this? So we only talked about
stationary increment.
So we had this one, and the increments were independent, and they followed the Gaussian distribution, right? So in that case, the additional thing was that they are
Stationary.
now in this case it was that they have to be independent and follow the Gaussian distribution. Let me just check here quickly. If we, I think stationarity is covered. Let me just check. And then for no, that is fine. The stationarity condition is already covered in the third condition of Wiener. If you read that, it says the increment xt plus h minus xt has a normal distribution n0 sigma square h. The distribution depends only on the lag. Is normal and depends only on the lag, which already covers stationarity. So then how is Wiener different from Levy? Firstly, Wiener has this. Wiener's by definition, the third one, the way we wrote it, that the increment xt plus h minus xt should have a Gaussian distribution sigma square h. You can already see there is no t in here. So the increments are stationary and Gaussian. And we already said in the second condition of Wiener that they had to be independent. So notice this is there, this is there, this is there. Then what's different? There is an additional thing that they have to be Gaussian. Levy doesn't require that, right? So if you put a fourth condition on this thing, within this thing the increments are Gaussian. If you want to put an additional condition here, then the process becomes Wiener. So then who is a subset of the other?
Levy is a subset of
इस जब restriction बनती जाती है तो सेट छोटा होता रहता है बड़ा होता रहता है. Wiener is a subset of. Levy is saying I don't care. Just satisfy these three conditions and you are in. You are Levy, right? Wiener is saying okay, I will satisfy all three, so I am in, and I will require this additional thing. So now I am unique within that. Yes.
सर ये कंडीशन लेवी के ऊपर है ना गॉसियन वाली.
नहीं ये मैंने ब्रैकेट में लिखी है कि अगर इस पे आप एक और डाल दें
तो
फिर Wiener होता है. हाँ आप फिर ठीक है. Yes. मैं ये कह रहा हूँ this is Levy. Yeah. Now Wiener satisfies all three, so it enters the Levy class, and then it says I want something additional. Similar thing you saw in counting processes, right? Counting processes में क्या था? There is a counting going on, right? And the increments are IID. That any process that satisfies this is a counting. Poisson said, okay, I will satisfy this condition with the additional thing that the gaps will be exponentially distributed. That additional condition made it Poisson process, which was still inside the counting process. Similarly, Wiener has its special condition, which is within, or which first satisfies all those, then an additional condition, and with that it becomes a subclass of Levy processes. That's the last note, that Levy processes are basically a very large class of continuous time, continuous processes, and we often use them to model situations where there are intervals of very small change followed by or interspersed by abrupt changes. So if you see a random process and it's doing things like this, first in many intervals there are very gradual changes, okay, it's like very small changes and suddenly there is jump, then there is a long period of small changes, then suddenly there is a jump, then there is a period of small change, then suddenly there is a jump. This kind of thing we normally, if you observe this and you want to model it, one thought should be, okay, this looks like a Levy process. Okay, it's just application note. You can of course, it's not so easy to just look at a process and say how I'm gonna model it. There's whole field है ना तो पूरा, लेकिन at least you get some idea. Okay, so this completes our discussion on the two special processes that we picked for our discussion, the Gaussian and the Poisson process. Or I hope that in the process of discussing these two processes you learn many new terms, and उससे फिर related processes भी उनकी debate में आ गए. Of course I am not claiming that after reading this you know everything about Levy or self-similar, right? पर ज़ाहिर है एक कोर्स में इतना ही हो सकता है जो connections आपको नजर आना शुरू हो जाए, you start seeing the connections, the overlaps, the classes, and then when you need to use them in another course or in your research, it will be easier. They will serve as a starting point, right? Okay, so that's my presentation.